Is intelligence necessary to survive in a simulation? If so, how does it evolve? Today we study the emergence of intelligence in a simulation with simple rules. Fish need to eat to survive and to reproduce. Offspring will receive the traits of their parents, with small changes in their genes and in their brain. In previous videos, I programmed simple neural networks that could only mutate their connection strength, not the shape of the network. In this version of the simulation, the structure of the brain can also change, which leads to smarter fish with more interesting behavior. Or at least, sometimes. Previously, we saw some fish roaming here and there, but most behavior was actually focused on finding food locally. Most fish would swim in circles until a food pellet appeared, and then go for it. With our updated brain, and by letting the simulation run for a couple of hours, we see that herbivores mutated to become expert navigators that roam the map in search of food and rarely hitting any walls. What's also interesting is that very often, not all fish need to evolve complex neural networks. The scavengers very often maintain a very simple neural network, and they have no need to become smarter. They are the sharks in the simulation, perfectly adapted to survive in their ecosystem with minimal intelligence. The competition for herbivores is more intense, and the pellets are less nutritious. So it seems that for herbivores, they need to evolve a smarter brain to navigate the maze of rocks faster in search of food than the other ones, so they become smarter over time. What's also interesting is that carnivory does not evolve in this simulation. Most likely, the initial neural networks are too simple to have carnivory, and as they get more complex, the herbivores get too fast to be caught. And so there is really no path for any omnivore to evolve into a carnivore. Next, we'll dive into the details on how these neural networks are built from the ground up and process information. Don't forget to like and subscribe if you like this. This helps out my channel a lot so that I can keep producing these types of videos for you. So, let's dive into how these neural networks work. So let's start with the concept of a basic neural network. A neural network has input nodes, there are 2 in this example. This one has 5 middle neurons, only 1 layer in the middle, and then 1 output neuron. So in this example, we want to get the angle where the fish has to swim towards as the output of our neural network. And the information we feed the neural network is the distance and the alpha, which is the same as angle, to the nearest pellet. In neural networks, very often you want to normalize the input. So you want to keep everything around 0 or 1. And so for the nearest distance, we take the maximum view distance of the fish, and 0.5 is exactly half of that. Same for the alpha or angle. Here the value will be between 3.14 and minus 3.14, since it's in radians. Next, let's look at the connections of every neuron. So as you see, in this example, the first neuron of the second layer is connected to both the first layer nodes. And it has specific weights. In this example, it's 2.0 for each for easy calculation. But usually these weights are between -1 and 1, and they're randomized at the beginning of your simulation or a training session if you're doing AI. So what you do for every node on the second layer is you take the input neuron value, multiply it by the weight, and sum that up for all the input connections. So in this example, we do 0.5 times 2.0 is 1, plus 1.0 times 2.0 is 2, and totals 3. So we have calculated the value of the first node in the second layer. We will do this for every single node in the second layer, and then we'll do the same for the output layer. So we have calculated the output, and the output is 0.85, again in radians, and so this fish will turn towards that pellet, which was at an angle of 1 radians. You see that sometimes fish don't turn exactly to where it goes, but as they come closer and closer, they actually come closer to the pellet or the other food source. How do these fish learn? So let's go back to our simple example where we just look at one node in the second layer. What happens in every generation of fish is that we make small mutations to the weights of the neural network. And this way, we can actually change on how it performs. And some fish will actually be better at going towards the pellets, and some ones will be worse. But the ones that are better will actually pass on the genes to their offspring. And that's how over time our fish get better and better at surviving, thriving, reproducing, etc. And so in the previous simulation, we actually had 10 input neurons, 5 middle layer neurons, and 4 output neurons. And they performed okay, but sometimes they were stuck locally because they tend to swim around in circles instead of roaming the map to search for food in other places. And so they were not that intelligent. So I've made some changes to the new neural network. I used a technique called neuroevolution of augmented topologies, or NEAT in short, to not only evolve the weights from generation to generation, but also allow for new connections and new nodes to form. So now the fish start with a very simple neural network with the same amount of input neurons and output neurons as previously. We also spawn them with 4 random connections, so not all nodes are connected. And then what we do over time is that on every new generation has a small chance to not only mutate the weights, but also create a new connection and a new node in a connection. So over time, this whole structure of the neural net changes and becomes more complex as the fish become more intelligent and adapt better to their environments. Thank you so much for watching. Don't forget to like and subscribe if you enjoy this type of content, and I will see you next time.